Hello, my name is William Schwend, and I'm a PhD student in the Autonomous Vehicle Systems Laboratory at University of Colorado Boulder. Today, I'm going to be giving a presentation on my paper, Hub Reaction Torque Reduction for Spacecraft Control using Robotic Arm-Mounted Thrusters. In recent years, the need to extend spacecraft lifetimes, assemble larger on-orbit structures, and upgrade existing assets has driven growing interest in in-space servicing, assembly, and manufacturing technologies. Many of these missions require spacecraft to operate in close proximity to a target vehicle, and robotic arms are a key enabling technology for these operations. These arms can be used to grapple a target spacecraft, support inspection, or perform servicing and assembly tasks. However, the inclusion of these arms on spacecraft raises a broader question. Can the robotic arms already present on proximity operation spacecraft be used to support spacecraft control? One way to use robotic arms for spacecraft control is to mount the spacecraft's thrusters on the arms themselves. In a traditional fixed thruster configuration, the available control wrench is determined by the spacecraft's geometry and fixed thruster directions. This is as simple from a dynamics and allocation perspective, but it can require many thrusters for full 6 degree of freedom control. Fixed layouts can also lead to inefficient thruster firings, when the thruster directions are not well aligned for the commanded wrench. The image on the left illustrates this, where opposed thrusters are firing and partially canceling one another in order to actually achieve the desired control wrench. Arm-mounted thrusters allow the spacecraft to reconfigure the thruster locations and pointing directions before firing. This can reduce the thrust cancellation and potentially reduce the overall number of required thrusters. The trade-off is that the control authority now depends on arm configuration. So changing the control wrench requires arm motion, which then couples back into the spacecraft's overall dynamics. The key challenge with arm-mounted thrusters is that the control wrench now depends on arm configuration. During proximity operations, the commanded wrench is updated frequently, so the arms may need to rapidly reconfigure between thruster firings. This reconfiguration induces reaction torques on the spacecraft hub, which, if left uncompensated, can disturb hub attitude pointing and degrade our overall pointing accuracy, which is especially problematic when the spacecraft must maintain line of sight to the target vehicle, either to accomplish its mission objectives or to ensure safety. To address this concern, a cascaded control architecture was previously developed. In that architecture, the inner loop separates the maneuver into a joint articulation phase and a thruster firing phase. During joint articulation, a prescribed hub torque is applied to counteract the arm-induced reaction torques in real time. This allows the hub to preserve pointing while the arms are moving. The cascaded control architecture was able to achieve strong performance in a representative close proximity inspection scenario, both in translational tracking and attitude pointing. This shows that the prescribed hub torque approach can preserve line of sight pointing during rapid arm configuration. The main drawback, however, is the size of the prescribed torques required to do this. Because the baseline joint controller receives a new desired configuration as a step command, the joints initially accelerate rapidly towards the new pose. These rapid accelerations can produce large transient hub reaction torques, which must be directly countered by our prescribed hub torques. The zoomed-in view on the right shows that these peaks are often short-lived and decaying by roughly an order of magnitude within just fractions of a second. Prior saturation results showed that the line of sight pointing can be maintained when the available prescribed hub torque is limited, but pointing performance does suffer degradation. This motivates the central question of this work, which is, can the required prescribed hub torques be reduced before relying on actuator saturation? To answer this question, we investigate two approaches. The first changes how the selected joint reconfiguration is executed. In the baseline case, each new desired joint configuration is applied as a step command, and the joint regulator drives the joints towards the command as quickly as the controller and actuator limits allow. This produces rapid joint accelerations, which generate large transient reaction torques, as seen on the previous slide. To reduce these transients, the step command can be replaced with a finite duration joint reference profile. The controller is converted from a regulation controller to a tracking controller so that the desired joint angle, rate, and acceleration are supplied as time-varying references rather than the single static reference of the regulation case. The goal is to spread the same joint motion over the profile duration, smoothing the reconfiguration and reducing the peak prescribed hub torque required to preserve pointing. The figure on the right compares the baseline step command with 3 finite duration profiles considered in this work: a linear profile, a cubic profile, and a quintic profile. These profiles impose increasing levels of endpoint smoothness to evaluate the impact of that smoothness on torque authority requirements. Reference profile tracking was evaluated over a range of profile durations from about 4 seconds to 9.5 seconds, with an outer loop duration of 10 seconds. The step command baseline is shown as having a 0-second reference profile. The plot on the left shows the distribution of the prescribed hub torque about the third body axis. The shaded regions show the interquartile range and middle 90% interval, while the line shows the median values. Introducing a finite duration profile substantially reduces the typical prescribed hub torque demands. For long duration profiles, we saw reductions of up to 80% relative to the step command baseline, showing that smoothing the commanded joint motion significantly reduces the torque required during most reconfiguration events. The right plot shows the maximum prescribed hub torques about each body axis. These peak values are especially important because they are what drive actuator sizing. The largest reductions occur about the second and third body axes, which are the dominant torque component cases in the baseline case. For the longer profile durations, the maximum prescribed hub torque can be reduced by as much as 98%. The torque reductions from the previous slide have to be interpreted together with the joint settling behavior. The left plot shows the settling time for each profile duration, where settling requires the joints to reach both the desired angle and desired rate tolerances before the end of the outer loop control window. For the cubic and quintic profiles, the settling behavior is predictable. The median settling time remains close to the commanded profile duration because both profiles enforce zero endpoint velocity. In other words, the joints are already commanded to come to rest at the end of the profile. The right plot shows the fraction of outer loop windows where the joints fail to reach the settling condition. For sufficiently long cubic and quintic profiles, it is evident that the missed windows can be completely eliminated. The linear profile behaves differently, however. Because it does not directly enforce a zero endpoint velocity, the controller typically needs additional time after the profile ends in order to bring the joints to rest. As a result, the linear profile produces longer settling times and a much larger fraction of missed settling windows, particularly as profile duration grows. The second method we evaluate to try and reduce prescribed hub torques evaluates which joint configuration is selected by the allocator. The motivation for this change is shown in the figure on the left. The blue bars correspond to the control periods associated with the largest 10% of prescribed hub torque magnitudes, about the third body axis, while the gray bars correspond to the remaining 90%. Across all joints, the large torque cases correspond to larger commanded joint reconfigurations, and the same trend is observed across the other two body axes. This suggests that discouraging unnecessary joint motion may reduce the resulting hub reaction torque demand. In the baseline allocation problem, the optimizer selects joint angles and thruster forces by penalizing control wrench error and total thrust effort, as shown in the cost function on the screen. However, it does not consider how far the new joint configuration is from the current one. The joint motion aware allocation adds the penalty term shown here, which penalizes motion away from the current joint configuration. This biases the optimizer towards nearby configurations when they can produce comparable control wrenches, reducing unnecessary reconfiguration between control updates. The joint motion aware allocation was evaluated by varying the motion penalty W theta, with a penalty of 0 representing the baseline allocation problem. All joints were weighted equally, so increasing the penalty increasingly biases the optimizer towards configurations near the current arm pose. The left plot shows the prescribed hub torque distributions about each body axis, while the right plot shows the maximum prescribed torque about each body axis. As the motion penalty is increased, the dominant second and third torque axes show decrease substantially. These results show that the allocator can reduce high torque transients by avoiding unnecessarily large reconfigurations. However, the trend cannot be taken on its own. The penalty is ultimately a tuning parameter, and if it becomes too large, the optimizer can become overly biased towards the current configuration rather than selecting the most effective arm pose, as we'll see on the next slide. The joint motion-aware allocation also changes the broader system behavior. As the motion penalty increases, the allocator selects smaller joint reconfigurations on average, so the joint controller can settle more quickly. In the left plot, we see that the settling time distribution decreases as we increase the penalty. And for penalties of 1e-5 and larger, the commanded motions settle for within the outer loop control window for all cases considered. However, the right plot shows that the penalty cannot be increased arbitrarily. At moderate penalty values, the total commanded thruster impulse decreases, which is consistent with the improved tracking behavior we observed in these cases. But once the penalty becomes too large, the optimizer is overly biased towards the current joint configuration. It then relies on less efficient thruster usage to produce the commanded wrench, which can cause the required impulses to increase sharply, as we see in the graph. Overall, this work evaluated two approaches for reducing prescribed hub torque, the prescribed hub torque required to preserve pointing during rapid arm-mounted thruster reconfiguration. The first approach changed how the selected joint motion was executed by replacing the step commands with finite duration motion profiles. These profiles reduced the maximum prescribed torque by up to 98%, though endpoint conditions strongly affected the joint settling behavior. The second approach changed which joint configuration was selected by modifying the allocation problem to penalize large joint motions. This reduced the maximum prescribed hub torque by up to 88%, but the penalty must be tuned because overly large penalties can increase commanded impulse and system error. In future work, we will evaluate the impact of spacecraft and manipulator design choices, including joint arrangement, arm mounting location, and manipulator geometry. We will also consider optimal or reactionless joint trajectories in order to further reduce the amount of prescribed hub torque required. In addition, we plan to incorporate minimum impulse bit constraints directly into the allocation problem, as that is one of the strongest benefits that a reconfigurable thruster array can offer. Overall, these results show that the actuator burden required to preserve pointing is strongly influenced by both the execution of the commanded joint motion and the allocation strategy used to select those arm configurations. This concludes my presentation. If you have any questions, please feel free to reach out to the contacts listed on screen. We'd be more than happy to answer them. Thank you.